Warning, the video you're about to watch contains mathematics at the level of pre-calculus. All material has an assumed prerequisite of college algebra and trigonometry. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is dedicated to factorials and combinations, really factorials, but combinations as well. You should have finished my video on Pascal's triangle and powers of binomials previously, and we're going to extend that, or actually this kind of takes an aside just for a brief moment, but it's necessary. We need this information so we can continue forward. Luckily, it's not too dense of material in this video. It's just about the factorial and combinatorics a little bit. So what is a factorial? Well, before I get into a factorial, even though you can read it down below, just note there are a lot of shortcuts in mathematics. So instead of writing 3 times 3 times 3 times 3 times 3, we invent a shortcut called a power, an exponent, and we call that 3 to the 5th. That little exponent is a shorthand for saying multiply 3 by itself 5 times. Well, just like we have that shortcut, we have another shortcut. If you said, I want 1 plus 2 plus 3 plus ... all the way to 10, we have a shortcut notation for that. It's the summation n equals 1 to 10 of n. We just add the number n starting at 1 to itself and every time increment until we get to 10. N becomes 1 plus n becomes 2 plus n becomes 3 all the way till 10. So again, lots of fast notation. Well, a factorial is the same style of fast notation. The product of the first n natural numbers is denoted using n with an exclamation mark, and this is called n factorial. N factorial is equal to n itself times the next number below it, 1 unit below, times the next number 2 units below, all the way until you get down to 1. And finally, just for convenience, because we need it, 0 factorial is defined to be 1. That's critical. So 0 factorial mathematically doesn't quite make sense, but we define it to be 1 because we need it to be 1 for other computations. So let's see how this works. 5 factorial. I'm just asking us to compute this. Well, 5 factorial by definition is 5 times 4 times 3 times 2 times 1. Notice the factorial notation's much faster, right? Writing 5 factorial rather than writing 5 times 4 times 3 times 2 times 1. That's why we use it. It's a shorthand, it's a lot faster. But this will be, let's see, 20 times 6 or 120. And you deal with factorials enough in mathematics as you move forward that you get to know these numbers very quickly. Nothing beyond 5 factorial, honestly, maybe 6 factorial, possibly. But 1, 2, obviously 1, 2, 3, 4, 5 factorial, you should know those by the time you finish this section, really. Now, before I move to the next page, I do want to mention it's the product of the first n natural numbers. And this definition will change slightly, well, okay, significantly, when you get to Calc 2, because you can actually do combinatorics or combinations with fractions. When we get to that point, though, we'll have other mathematics we can rely upon, and we'll be a little bit more advanced with our thinking when it comes to factorials that we can manage that. But for right now, it will, for us, make no sense to ask what's 1/2 factorial. I guess it probably never makes sense to ask what's 1/2 factorial. Anyway, so let's compute this. 11 factorial divided by 9 factorial. So I'm just doing arithmetic right now. 11 factorial, well, that's 11 times 10 times 9 times 8 times 7, right? I could do this for a while. I don't want to, so I'll just stop there. And 9 factorial is 9 using a different color, times 8, times 7, times, and so on and so forth. And you could see between the numerator and denominator, things cancel very quickly. 9, all the 9, 8, 7, 6, 5, 4, 3, 2, 1, they cancel beautifully. And this becomes 11 times 10, or 110. This kind of gives a big hint as to when you're working with factorials. 11 factorial over 9 factorial, you could have written that as 11, that is not an 11, that was where my brain was going, 11 times 10 times 9 factorial over 9 factorial. That's a good way to do it, where you kind of take out the first two natural numbers in that multiplication, and then you have the 9 factorial saying, oh, and then 9 times 8 times 7 times 6. Okay, and then you can cancel those. It makes the mathematics fast, right? But what if you're dealing with something that's not a given stated number? And by the way, I should probably mention here, n is in the natural numbers. N is greater than or equal to 2, and n is in the natural number system. All right, so how would you deal with this statement, not knowing what n is? Well, basically the same way we just wrote that last example. We know that n factorial is n times n minus 1 times n minus 2 factorial. It's n times the next number below it, times the next number below that, times the next number below that, and so on and so forth. But we don't have to actually write all of them out. We can just decide, you know what, I've just popped out the first two numbers there, and I got tired, so let me use a factorial for the rest. Well, these two factorials in the numerator and denominator will cancel beautifully, and you get this wonderful 1 over n times n minus 1. Again, factorials technically are only defined for natural numbers, so you can't really do this for fractions. So it's not that every single time that you see these, they'll cancel. Well, no, actually they will. With factorials, they will cancel nicely. But why learn this if it's only just a convenience, right? A numerical convenience. It speeds up a little bit of computation. Well, that alone is actually good enough to learn it, I think. It's the fact that it speeds up handwriting, stuff like that. Mathematicians, we're notoriously lazy. We really try to reduce the amount of writing down to the bare minimum if we can. And so how can we use this in other respects? Well, one thing is the binomial coefficient. Now, for right now, ignore the name, because it's not going to make sense until we link things together. But for right now, we'll just say, here's a definition. It is actually the binomial coefficient. But again, you wouldn't know that until a while from now. So let's go ahead and just talk about this. Let n and k be non-negative integers. In other words, they're natural numbers, but they could also be 0. And we're going to allow k to be less than or equal to n. That's kind of critical for this definition. The binomial coefficient is denoted with this notation. It's not a fraction, although we'll all, myself included, have a habit, or not a habit, but have a tendency of writing a fraction bar there, because every time you write a number over a number, you tend to want to force in some type of bar there. But it's not a fraction. It's just n stacked over k with parentheses around it. And it is defined, that notation is defined to be the following quotient of factorials. N factorial over k factorial times n minus k factorial. Now, a few things I want to mention here. How do you say this? How do you say that notation? How do you read that? Well, the way that I have a habit of reading it, I call this n choose k, and that's from probability. And I'm sure there's another way of saying it, but that's just the way I'm always going to say it. So I'll write that down. And mathematically, the value that it becomes it's a little bit easy to remember if you think, well, the n goes in the numerator with a factorial, so does the k. The k goes in the denominator with a factorial. So it's like an n factorial over k factorial, but then you have this offset right here, the n minus k quantity factorial. Well, if you added up this k to that factor right there, k plus that n minus k would be n. So when you see this in practice, it's really very nice, because if I said what's 5 choose 3, mathematically that's 5 factorial over 3 factorial. And the big question is, what do I put in? I know I put something else in that denominator. Well, it's just this 5 minus that 3. That's all it is. So it's 2 factorial. That's a really good, fast way of thinking about it. All right, that all being said, what the heck does this mean? Because is it just some special computation that they teach us for no reason? Well, there's a lot to it. This delves deeply into combinatorics and probability theory, which is not what we're going to get into, even though that's an awesomely awesome subject. I'll read this verbatim. The binomial coefficient actually has several different notations, but the most common are n choose k, the one that I had written there, and then nck, which means n choose k. Numerically, it is equivalent to computing the number of ways to select k items out of n without worrying about order. What do I mean by that? I mean, like, if you had, let's suppose, that you only have 5 friends or 6, sorry. You have 6 friends, but you can only take 1 to a party. Well, how many choices do you have? In disregard that you might have friends that you favor over other friends. Just say they're all equally, they're equivalent as friends to you. They're all your best friends, okay? But you can only take 1. So it's like a random lottery, right? How many choices do you have? Well, you have 6 choices. So there are, out of 6, to choose 1, you could choose either person A, person B, person C, person D, person E, or person F. Those are your 6 choices. Now, that tells me that 6 choose 1 should be 6. That's what that notation actually means. If I have 6 friends and I can only choose 1, how many choices do I have? Well, you can choose friend A, B, C, D, E, or F. So you have 6 choices. Let's see if that works out mathematically. Is that 6 factorial over 1 factorial times 6 minus 1, which is 5 factorial? Well, let's see. 6 factorial is the same thing as 6 times 5 factorial. Let me erase that. Well, it's not erasing, so whatever. It's the same thing as 6 times 5 factorial. 1 factorial is just 1 over 5 factorial. And notice the 5 factorials cancel. And this does become 6. So it checks out. Okay, that's kind of cool. Great way to think about this. What if we change the question and we say we have 2? We have our invite and then we have 2 additional invites. I could take person A and B, or I could take person A and C. So let me show you all these combinations I could take. And order doesn't matter. So taking person A and B is the same thing as taking person B and A. So let's see how many combinations we have. I could take A and B, or I could take A and C, or I could take A and D, or I could take A and E, or I could take A and F. Well, that's, let's see, 1, 2, 3, 4, 5 choices there. Now let's talk about, had we taken person B? We could have taken person B and C, or B and D, or B and E, or B and F. So that's 1, 2, 3, 4 other combinations there. Now let's talk about person C. We could have taken C and D, or C and E, or C and F. That's 3 choices right there. Notice I didn't say what about C and B, because C and B have already been taken care of in the black ink. Now let's talk about person D. D and E, or D and F. 2 choices there. And then finally, person E, you can take E and F. That's pretty much it. So 1 choice there. If you add up those numbers, 5 plus 4 plus 3 plus 2 plus 1, which is, by the way, a summation formula we happen to know from a previous section, that'll be 5 times 5 plus 1 over 2, and that's going to be 15. So notice I actually have several ways I could have computed this, first of all. Second of all, when I got down to this 5 plus 4 plus 3 plus 2 plus 1, I could have computed that using arithmetic. 5 plus 4 is 9, plus 3 is 12, plus 2 is 14, plus 1 is 15. Or I could use my series, and that is very useful. Just to remind you, that formula is this guy right here. And I mentioned in the video on summations that this is one of the most popular sums in calculus, actually in mathematics, to be very honest with you. And the proof was attributed to Gauss. I don't know if that rings a bell for you. But anyway, this summation formula is very powerful if we had a large value of n. So if I was adding up not 5 plus 4 plus 3 plus 2 plus 1, but 2011 plus 2010 plus 2009 plus 2008, it's just that formula right here is much faster. It's just a product of two things divided by 2. And then we could have done all that to get to the 15, or we could use this new notation. We have 6 friends, we can only choose 2. So 6 choose 2 is 6 factorial over 2 factorial times 6 minus 2, which is 4 factorial. Well, 6 factorial is 6 times 5 times 4 factorial. 2 factorial is 2 times 1. 4 factorial is 4 factorial. Notice the 4 factorials cancel. And you have 30 over 2, which is 15. And now you can see why that notation's awesome, because it really does speed up these conversations. It gets very, very difficult if you have, let's say, 20 friends and you want to take 7. There's a lot of combinations. It was bad enough when we had 6 friends, we want to take 2. Look at all those spider webs right there. So it can be very daunting if you do this by hand without the choose notation. That choose notation is very, very powerful. So rewinding the tape and starting at the beginning, calculate the following. You have 6 friends, you want to choose 1. Well, we just did this, but let's just do it cleanly. 6 choose 1 mathematically is 6 factorial over 1 factorial times 6 minus 1 factorial. And of course, 6 factorial, 6 times 5 factorial over 1 times 5 factorial, and the 5 factorials cancel. I want to do this for a very specific reason, because we're going to expand upon this. So 6 friends, you get to choose 1, you have 6 choices. What if you want to choose 4 friends? If you had 4 friends to take? So let's see what happens. 6 choose 4. Well, that's 6 factorial over 4 factorial times 6 minus 4 factorial, which is 2 factorial. Notice that denominator, 4 and 2 would add to that 6 upstairs. That's a good way to think about it. 6 factorial is 6 times 5 times 4 factorial over 4 factorial times 2 factorial is just 2. And the 4's cancel. That's 30 over 2. It's 15. Wait a second. Didn't we just see that right here in our introduction? 6 friends and you choose 2 of them to take to the party. There are 15 options. That's the same as choosing 4 people to take to the party? Well, of course it is. It's totally the same. Why would I say, of course, that this is the same as 6 choose 2? It's because choosing 4 people to go is the same thing as choosing 2 people to not go. So that's why those are the same computations. And by the way, this holds as you increase the number. So if you had 100 friends and you want to choose 4 of them for a party, that's the same thing as having 100 friends and choosing 96 to go to a party, because you're choosing 4 to not go. So they're the same computations. There's a symmetry about it. And that's a very provable theorem that we'll see in a little bit. Okay, so suppose you have 6 friends and somebody says you can't take any of them to the party. how many ways can you choose nobody to go to a party? Now, there's only one way to choose nobody. Just choose nobody, right? So that should be the number 1, but let's see if that mathematically turns into the number 1. 6 factorial divided by 0 factorial times 6 minus 0 factorial. Well, the 6 factorials cancel beautifully. And 0 factorial, remember, is defined to be 1. So there is only one way to choose nobody. By the way, as we said earlier, as I said just a moment ago, this should be the same as you have 6 friends and you could take 6 friends to the party. So how many ways can you grab those 6 friends? There's only one way. You grab all 6 friends and go. And by the way, that last example was actually a theorem. N choose 0 is equal to 1. I have proof here, but really it's not much of a proof. You start with n choose 0. It's defined to be n factorial over 0 factorial times n minus 0 factorial, which is going to be 1 over 0 factorial, which is 1 over 1, which is 1. QED. Not very much of that proof. That type of proof is what my students would love on an exam. That's not going to happen. And here we get to larger numbers. You can totally do this. You have, let's say, 50 objects, and you get to choose 4 of them. Let's say you run a duck sanctuary, and you have 50 ducks, and you're choosing 4 of them to be in a duck contest. This is a silly example. Anyway, how many choices do you have? This is what would be the number of choices you have. 50 factorial over 4 factorial times 50 minus 4, which is 46, factorial. Well, obviously 50 factorial is 50 times 49 times 48 times 47. And then when I get to the 46, I know that's a 46 factorial downstairs, so I'll just leave it like that. 4 factorial, I'm going to write as 4 times 3 times 2, technically times 1, but whatever. And we have a 46 factorial. And then we can cancel the 46 factorial. And at this point, I just start going through and finding things that go into numbers, right? 4 goes into 48 12 times, and then 2 goes into 12 6 times, and 3 goes into 6 2 times. I mean, that's probably the easiest way to do that. And everybody knows that 2 times 50 is 100, and that 49 times 47 is 2303, because everybody totally knows that. And you multiply those two together, and you get 2303 with a couple zeros at the end, to 230,300. So there are over 230,000 choices or ways to choose 4 ducks out of the 50. There you go. This kind of illustrates what happens as you introduce more options. It gets ridiculous that these number of choices start to explode, right? So this is why when you go to play the lottery, and I don't play the lottery because it's a tax on the poor, but if you play the lottery, which you shouldn't, because statistically speaking, you're not going to win. But if you play, then you know how many choices you have for numbers to pick. I don't know how many there are. Let's just say there's 65. And you pick 6 of them. Well, how many options of numbers are there, right? So how many ways can you pick numbers? And there's only one winner, right? And so this is 65 factorial. I'm not saying that there's 65 choices. I just can't remember how many choices there are. Over 6 factorial times 65 minus 6, which is 59 factorial. And so that would be 65 times 64 times ... all the way down to 60 times 59 factorial over 6 times 5 times 4 times 3 times 2 times the 59 factorial. And you'd cancel these out. 6 goes into 60 10 times, 2 goes into 10 5 times, 5 goes into 5 nicely. I'm sure there's some other numbers here, like 4 I think goes into 64 16 times, right? And then 3 goes into one of these other numbers, I think 63. But let's compute this out. And I just had to grab a calculator to do it. It is not approximately, but exactly 82,598,880. So let's put some comment. 82,600,000 choices. So what's interesting about the lottery is that, and this is not obviously a conversation about the lottery, but it's always nice to engage with real world mathematics every once in a while. A lot of people, if there are 6 numbers to pick for a lottery and you tell somebody, I'm going to pick these numbers, these are my favorite numbers, people will laugh at you and say those numbers will never win. And your response should be, they have the same probability of winning as yours. They really do. Those numbers have the same likelihood of winning the lottery as your favorite 6 numbers. So usually that example puts things into perspective. Like, what's the probability that those 6 numbers, that's not going to happen? Well, neither are yours. So that's how that works. By the way, a lot of people play those numbers. So don't play those numbers, because that means you'd share your prize with a lot of people. By your prize, I mean the prize you're never going to get from playing the lottery. All right, so this is 50 choose 46, but we happen to know something about 50 choose 46. It's the same thing as 50 choose only 4. And we just computed that in the last example. It's 230,300. Again, they're the same because choosing 46 of your 50 friends to go to a party is the same thing as ignoring 4 of your 50 friends. Picking which 4 you're going to ignore is the same as picking which 46 you're not going to ignore. So there is that symmetry with the choose notation. And here is the theorem that actually states that n choose k is the same thing as n choose n minus k. That's that symmetry statement. So 50 choose 4 is the same as 50 choose 50 minus 4, which is 46. That's what this theorem is stating. So we'll call it the symmetry theorem. That way it's at least stated in there. I'm just making that up, by the way. It's binomial symmetry theorem. But now that I've said it, you guys are going to spread the word, and we'll make it a thing. We're going to make this an internet sensation. It'll be the next K-pop. All right, so let's go ahead and prove this theorem. It's a very fast proof. N choose k is equal to n factorial over k factorial times n minus k factorial by definition, which is the same thing as n factorial over n minus k factorial times k factorial, which obviously all we did was use a commutative property of multiplication there. But now I'm going to do something kind of funny. Not funny, haha, just funny, interesting. I will rewrite that k factorial as n minus the quantity n minus k, n quantity factorial. I sincerely hope that you agree that k is the same thing as n minus k. That negative would distribute and become a negative n and a positive k. The n's would cancel and you get a positive k factorial. Those are the exact same statements. And by the way, this is the definition of n choose n minus k. It would be n factorial over n minus k factorial times n minus k factorial. So there you go. It has now been proven that n choose k is the same thing as n choose n minus k. And now we get to the final example. There you can do arithmetic with these binomial coefficients, and it just takes getting used to working with choose notation. We do know a few things here that will help out. First of all, 6, maybe I should write it this way. 6 choose 0 is the same thing as 6 choose 6. Again, choosing none of your friends is the same thing as choosing all of your friends. It's the same number of choices, 1. 6 choose 1 is the same thing as 6 choose 5. Oops, equals 6 choose 5. And again, choosing one of your friends is the same thing as choosing 5, because choosing 5 friends is the same thing as saying Which friend am I not going to choose? 6 choose 2 is the same thing as 6 choose 4. So if I highlight the things that are the same, those two are the same. Let's see, these two are the same. They don't cancel because you're adding them up. They just double up. And these two are the same. The middle one is kind of the oddball because there's nothing that matches that. So we really have twice, this summation is twice 6 choose 0 plus twice 6 choose 1 plus twice 6 choose 2 and then plus 6 choose 3. All right, well, we've computed all of these except for 6 choose 3. How many ways can you choose nobody? There's only one way. 6 choose 0 is just 1. Remember, n choose 0 is 1. Plus 2 times, how many ways can you choose one person out of 6? Well, 6 ways. Plus 2 times, and then we did this one earlier. 6 choose 2. Let's see if I can find it. It's right here, and it was 15. It says, oops, except you don't want to scratch it out. You want to highlight it. It's 15. 6 choose 2 is the same thing as 6 choose 4, and it was 15. And finally, we have 6 choose 3, which we have not computed. So 6 factorial over 3 factorial times 6 minus 3, or 3 factorial. Let's go ahead and simplify all this stuff. That's 2 plus 12 is 14, plus 30 is 44. Plus, let's see, 6 times 5 times 4 times 3 factorial, which cancels with one of the 3 factorials downstairs. And then 6 times 2 goes into, 3 times 2 goes into 6. And so we have another 20 we're adding to this 44. That is going to be a 64. There's going to be an interesting pattern about this style of summation we're going to notice in the next video. But for now, we're done with this one. All right, see you next time.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.